So now we are going to cutting fluid applications in machining region. How we have to apply the cutting fluids in the machining region we will see now. Till now we have seen the comparison between eco-friendly cutting fluids as well as mineral oils. What are the rheological aspects, what is the flowability, how the capillary action takes place and all those things. Thermal aspects also we have seen, and we also see the thermal aspects. I mean to say that conductivity and specific heat of the cutting fluid and all those things we also see here as an integral part of some subject. At the same time we also see in the biodegradation, how the biodegradation will takes place between mineral oil as well as biocutting fluid. If we have seen all these things from the cutting fluid composition point of view, and now we have to see another aspects how to improve the performance. For that purpose we are moving into how precisely we have to apply and what are the parameters that we have to consider. That particular aspects we will see in this lecture. Okay, so minimum quantity cutting fluid, it is one of the best techniques. So we will see about introduction to minimum quantity cutting fluid and how economically we can develop this system, and commercially what are the available nozzles, how to decide, and the MQCF parameters, what are the parameters that will decide the performance and all those things. What are the minimum things that one should take care scientifically so that he can come up with a better solution for the performance point of view as well as from the ecological point of view. So cutting fluid composition, here we will see the thermal conductivity experiment. Again we will go through just some glimpse. At the same time we will also do the standoff distance, how far we have to keep it, and the nozzle angle, at what the nozzle angle we have to do. So these are all about the minimum quantity cutting fluid. Some of you may not have present in the previous lecture. Let me brief you that minimum quantity cutting fluid is best process compared to the flood cooling process. Okay, so if you have not seen, you can just go through the videos. What is the comparison between minimum quantity cutting fluid as well as flood coolant, and then you can read about this one, or you can go about this one. Then we go for the practical comparison of flood cooling process with respect to minimum quantity cutting fluid. This particular chapter mostly we deal with those research oriented papers, not with respect to the introduction that is available in traditional books and all those things. So most of the people who may be interested in taking up this job as their project work, they can clearly follow how the things are working, how you have to choose scientifically and all those things. The shape of the machining region and the chip tool interface. The first and foremost thing is, what is the shape in the machining region? If you see the tribological aspects, this is a picture is known to you since I have shown one or twice in the previous. If you see the machining region where the chip tool interface is there, this is the region where chip tool interface is there. So the chip is moving on the rake surface, and it has a sticking region as well as sliding region. And if you see the three-dimensional surface profile of the cutting tool, this one, this is the 3D surface profile. Okay. Here normally what is the sticking region? Mostly we are concentrating about the sticking region and sliding region slightly. So the aerial is a elliptical shape. Normally if you see here, it is a elliptical shape where it will have a minor axis as well as a major axis. So let me draw this in outside. If you have a elliptical shape, you have a minor axis, you have a major axis. Okay. So then which is important for you? Whether it is a minor axis is important or major axis is important from the cutting fluid application, since you are going to apply your cutting fluid in this direction. Let me slightly erase some other material, previous material. So you are going to apply the cutting fluid in this direction. So like this. In that circumstances, I am mostly worried about my minor axis. How to reduce my minor axis? That is the concern. For that purpose, how we have to go about and choose various parameters and all those things. That is what about the this particular class revolve around. So various eco-friendly cutting fluids, if you have seen, this is just a glimpse compared to mineral oil based cutting fluids, sunflower oil, coconut oil as well as canola. Then you can also look into the liquid nitrogen and all those things. But liquid nitrogen, if you are going from the point of economy, it may not be economic. So you always can go with the eco-friendly cutting fluids, which are vegetable-based cutting fluids. Any combination of these vegetable oils, you can go ahead and you can form your own cutting fluid, or there are commercially available bio cutting fluids are there, you can procure it. Okay. If you see here, there are the solutions. Flood cooling technique, high pressure coolant technique. This is the flood cooling technique. This is the high pressure cooling, and this is the cryogenic cooling. This is MQL or MQCF. So basically we go for MQCF because normal in flood cooling is 400 to 600. That means average it is will be 500 ml per minute. In that circumstances, lot of emissions will take place. Consumption of cutting fluid also have 15 to 17% of the product cost. In that circumstances, normally we have to minimize the cutting fluid, but we have to maximize the performance. For that purpose, if the heat transfer performance factors, we have seen heat transfer, lubrication, flushing action, mist generation, corrosion inhibition. These are the things that also we have seen. And most importantly, you have to generate this MQCF, that is the minimum quantity cutting fluid set at the economical price and all those things, so that it will be environmentally friendly as well as it should not cause health hazards. Looking at all these aspects, we can design our system for economic as well as the product cost should be low and the performance should be better. For that purpose, we are going towards minimum quantity cutting fluid. So minimum quantity cutting fluid, normally to make the more sustainable. Sustainability can be defined in three ways. One is it should be economically friendly, environment friendly, and the third one is social friendly. Economical friendly means it should be less cost. Environment friendly means it should not cause any type of emissions or something. At least it should emit minimum emissions. Social friendly means it should not harm the end user. Basically, assume that I am making a rod with sharp edges. What will happen if during usage, operator or any common man who is using it, he may hurt his hands and fingers. That should not be. So that for that purpose only, normally radiusing and chamfering will be given. So that is one of the examples of social friendly and all those things. Minimum quantity lubrication refers to the precise dispenser to the supply of meniscus, normally 5 to 500 ml per hour. This is completely, if you see per minute in a flood cooling, it is 500 ml per minute. So here normally 5 ml per hour. So it is very minimal. So 15 to 17% of the product cost that you are spending will be enormously reduced, so that your product can be competitive in the market. Over 2 billion gallons of cutting fluid is wasted per year using flood cooling, basically flood cooling technique. So 17%, already I said this is the reference, where 17% of the manufacturing cost is attributed to the cutting fluid. But about the waste disposal accounts for 54%. That means that whenever you are disposing your cutting fluid, in the recycling of cutting fluid, if you use in a flood cooling, you recycle it, and at last you may have to dispose it off to a near to river body, or you have to dispose it to soil wherever you are digging and all those things. So transportation cost is the one thing. At the same time, you cannot dispose like that. You have to do lot of post processings if so that you can dispose it off. So the post processings plus transportation and disposing, labor cost, these are all include in this one, disposal cost and all those things. This will be huge amount, rather than if you can use a minimum quantity cutting fluid technique where you just spray it, where the efficiency can be improved by the forced convection process. At the same time, penetration ability is better because of its atomization. So this is having many better things. At the same time, new technologies are coming up nowadays, but whatever this technology is around 2002 to 2010, nowadays also many people are using, and you can use this process for those people who want to carry out their work. And only thing is that how to optimize so that the operators as well as the company people will get economically benefited as well as environmental friendly benefited. That much thing one can take up as a work. So minimum quantity cutting fluid advantages: it is environmental friendly with green and sustainable manufacturing process, no maintenance cost and waste, because just it is a spray that you just spray, it will goes off. So there is no recycling process, there is no transportation, post treatment of disposals and all those things. Lower thermal shocking for the workpiece materials because thermal cooling will take place by the forced convection. Less clogging of the wheel, that is represented to a grinding operation, which we come across in the upcoming classes in where we study about honing process, super finishing process, most importantly grinding, where surface grinding, internal grinding, external grinding, centerless grinding and all those things. And even you get the good surface finish. Surface finish is a qualitative statement. That means that you will get a low surface roughness value. So minimum quantity cutting fluid, the beauty about this one, as I said, easy accessing capability of air into intricate surfaces is the one of the advantage. At the same time, the coefficient of convective heat transfer of cutting fluid is high. So these two advantages. One advantage, if you see the one advantage, easy accessibility of air into intricate shapes, this we are taking. Assume that I have a flood cooling process where convective heat transfer coefficient of my cutting fluid is very high, but it cannot penetrate. In another case, air has low convective heat transfer coefficient, but it can penetrate. So the advantage of air, that is easy accessible to intricate regions, I am taking, but I am not taking the low convective heat transfer coefficient of air. So I am taking the high convective heat transfer coefficient of the cutting fluid, but its inability to go into the machining region I am not taking. So I am taking the positives of air, penetration. At the same time, I am taking convective heat transfer coefficient of the cutting fluid. Both I am mixing it, and I am coming up with minimum quantity cutting fluid technique. This is about the minimum quantity cutting fluid. If somebody has not followed in the previous classes, you can follow from this particular slide. So the minimum quantity cutting fluid, here you will have a atomized gas. It is not a liquid, it is a atomized gas that is made up of high pressure air plus cutting fluid, liquid. So both will mix and come. This mixing can be done in internal mixing as well as external mixing. I will come to that particular slide also. This will mist, which is a cutting fluid atomized mist, can penetrate and take out the heat by the forced convection process because you are sending with high pressure air. So minimum quantity cutting fluid, normally these are also called as near dry machining process. This one, because normally 1 ml per minute or 5 ml per hour, these are many techniques are there, depend on your nozzle type, mixing type and all those things. So if you are using 500 ml per minute in a flood cooling, if you are using 5 ml per hour or 1 ml per minute, this is nothing. that is near to dry machining, that is near to you are not using the cutting fluid. That's why this machining also called as near dry machining, or some people it is also called as pseudo dry green machining. Why it is called a green machining? Now you see the ratio of cutting fluid to the water is normally 1 is to 12.5, 1 is to 8, 1 is to 10 and all those things. Approximately 93% of cutting fluid emulsion is water. What if that is the case, whatever it will emit, the major amount will be like water vapor or something. So that means it is green, or you can say it is near green machining process. So that's why it is called as near dry green machining or near dry machining. You can say, people say minimum quantity lubrication, where they don't use the emulsions. Some people they say that micro lubrication, because the nozzles are specially designed, at the same time they are going to send the cutting fluid very minimally. So this is an economic way, because being a India a developing nation, many people come up some economical solutions. So the people who want to go and develop this type of setup, you can easily develop this setup. So if you can see, you need some of the components like compressor you need, and you need nozzle, where two nozzle you can develop, and in the system I will explain where twin hole nozzle you require, and cutting fluid tank. So what is you are going to do here is, your cutting fluid is coming from this pipe. You can see this pipe, this is a pipe which is sending my cutting fluid horizontally. At the same time, compressed air is coming like this, and both are mixing externally. Here we are using external mixing. External mixing, you might have already seen this slide. The external mixing is taking place by the virtue of pressure difference between your cutting fluid, which is coming certain height. Normally this cutting fluid is kept at a certain height. In the next slide you will see, from the machining region, by the virtue of gravity it is falling. At the same time it will also suck because of air pressure. Air you are sending at 5 bar pressure, 7 bar pressure and all those things. Because of the pressure difference that is generating here, one nozzle exit is like this, another nozzle exit is like this. Both here you are coming cutting fluid, another one here you are getting air, compressed air. So both will mix here and divert in this direction. So machining region is here. So in that way you will can generate the mix. You can see here mix. This is the mist that is formed, and from the machining the exit it will falling a diverging, so that you can design your system so that it will fall on my cutting tool. This is the cutting tool. This is about the machining system with minimum quantity cutting fluid, how the zoomed version look like. If at all I want to see the overview, how the overview it look like, this is the cutting fluid tank, this is, and you can have a graduated scale here. This is the graduated scale where the graduations are there. How you can measure the cutting fluid quantity, how much is flowing and all those things. This is the air pipe, this is the cutting fluid pipe, and this is the air, which is compressed air. Air is coming from this one. So this is the twin hole nozzle. And you are generating the mist and sending, which you can see in the previous slide. This is how the mist is generated from this particular setup. But the problem here is your workpiece is rotating at certain speed and there may be a splashing takes place. For that purpose, to keep the operator safe, what we have done a shutter where if there is any splashing also, it will fall on this one. At the same time, one thing is not visible here, that is operator is looking from this side. So this particular shutter has a transparent window which is made up of a perspex, so that the operator clearly can see what is going on in the machining region. At the same time, once the operation is completed, he need not to completely dismantle from the setup. He can just, if this is a hinge is there, you can see here it is a nut system, just you can lift that one and you can take out your work product. This is as simple as that one. This will be movable. So this is about how you can develop with the existing materials in a small scale laboratory also. This is cutting fluid tank made up of perspex. You can join this perspex by chloroform and you can make your cutting fluid tank. You can put a small scale where the graduations are there and you can connect this cutting fluid tank with respect to cutting fluid and compressed air pipe and compressor you can put at certain part of your laboratory and you can get the compressed air, and twin hole nozzle you can develop using your stove nozzles also. Just you make aluminum twin hole nozzle, just you fix it with your stove nozzles. That is what here the authors have done. And splashing protection you can also done by some of the aluminum based sheets and all those things. So this is about how you can develop economically, and you can also control the cutting fluid mist generation by this output pressure regulator. Okay, output pressure regulator knob is there, just you adjust output pressure regulator nozzle and you can also check how the cutting fluid is sucking and what is the particle size, that is a droplet size, and all those things also you can measure. The droplet size measurement and simulations and all those things we will see in the grinding. That is a part of grinding where we will see some of the simulations of some of the authors, how the particle generation with respect to atmospheric air pressure, what is the droplet size that is coming in the machining region from the minimum quantity cutting fluid and all those things we will see. These are the commercially available setups. If you see till now, what you have done is how you can develop in the laboratory, how with minimum cost you can generate. If at all you have some money, so you can go ahead with purchasing of the nozzles, where if you can see here the nozzle system which is cutting fluid is there, as well as you have the air is there, both are mixing internally and sending the mist like this. So this is one of the systems. At the same time you can have another systems also where you can mix internally and send the spray like this. Everywhere it is a spreading one. So different companies will produce different nozzles and the mixing mechanisms. These mixing mechanisms are patented by themselves. They can have the internal mixing, external mixing. In internal mixing also many varieties are there. So different nozzle systems are different varieties are mixing is there. Just you have to choose a right variety of nozzle for your application, so that your performance of the machining improves. At the same time, ecological aspects also considered during the performance testing. Okay, these are the nozzles. How normally you can see it is a 0 degree nozzle, 15 degree diverging, 25 degrees and 40 degrees. How these are practically shown during the machining operation, you can see here. So these are the nozzles. Nozzles will be given some of the colors, how to differentiate and all those things. So how this area, how much area it will fall and other things you can check from this one. You can choose if you are going for a turning operation, which one I want. If you are going for a milling operation, which one I want. If you are going for a grinding operation, which type of nozzles I want and all those things. This will help you in choosing a right nozzles for your application. Okay. These are the other varieties of nozzles which you have seen already. I want to emphasize two things. One is internal mixing as well as external mixing. That is, if the cutting fluid and air both are mixing outside the nozzle, that is called external mixing. If both are mixing internally, that means that within the nozzle system there is a mixing chamber will be there. If there it is mixing and coming the mist outside, that is called internal mixing. If it is mixing outside the nozzle, it is external mixing. It within or before the nozzle exit, if it is mixing, that is called internal mixing. There are varieties of nozzle designs. You can see I am just not going in detail about the nozzle mixing and all those things. If you see these pictures where the air is coming from here and cutting fluid is coming from here, both are mixing and here in this one internally as well as it is coming outside. The internal mixing operation is going on. So like that, many varieties of mixing technologies are there because companies have their own patented technologies. That's why they have different people will have different nozzle designs. Okay. So MQCF parameters, that is normally emulsion composition. Emulsion composition is one of the most important, and in this particular section I am just repeating some of the things that we have seen in the previous classes, that is thermal conductivity measurement, specific heat measurement and all those things. Just I will go through it, not in detail, because in detail I have already gone through. The stand-off distance, force exerted by the mist, that is varying nozzle stand-off distance from the stationary plate, area covered by the mist, and nozzle spray angular position. How these are affect the minimum quantity cutting fluid. We know that the minimum quantity cutting fluid is a better from the dry as well as flood cooling within MQCF. How to go for betterment of this MQCF? How to improve the process performance by using variables that are affecting the performance of MQCF. That is, one is emulsion composition and second one is stand-off distance, that is force exerted by the mist, that is stand-off distance. At the same time, how much area it is occupying. Third one is nozzle spray angle. These are the three. It looks like three, but within the stand-off distance also you have two more variables, that is how much area it is covering and what is the pressure it is, or what is the force it is exerting and all those things. Okay. If you see the minimum quantity cutting fluid composition itself is one of the thing. How to represent the proposed work. That means that if I am doing the minimum quantity cutting fluid in a scientific way, how to propose that particular part of work to explain, that is physical and chemical properties, emulsion composition. These are all things. Then minimum quantity cutting fluid, stand-off distance, angular position. Then we will go for the measurement of the forces, coefficient of friction. Then we go ahead with morphology of the surface in terms of surface roughness, tool wear, and sticking region, sliding region, and all those things we also see. The first one, we want to compare between mineral oil as well as biocutting fluid. For that purpose, the first and foremost thing that we are going to characterize is their pH characterization. If you see the pH characterization, the biocutting fluid and your mineral oil, normally the pH should be around 7. If it is around 7, there is no much problem. So among this biocutting fluid and mineral oil, near to 7 is biocutting fluid. That means biocutting fluid has good pH compared to the mineral oil. Density wise, the biocutting fluid has slightly high. If the density is high, obviously viscosity will be also high. And the flash point, if you see, it is good for the biocutting fluid compared to your mineral oil. That means that fire catching ability will be slightly less compared to your mineral oil. That means except viscosity, it is having all better. But if we have a viscosity in a good amount, that is higher side of viscosity, that means it will also give me good lubrication. From the point of lubrication also it will give. Let's see whether the statement is true or false or neutral, how it will going to in the upcoming slides. Okay, selection of optimum cutting fluid emulsion. Here I said how to select what is the composition that I want. This particular part I have taught already in the previous sections whenever I am teaching about thermal conductivity and all those things, emulsion composition and all those things. So water is known to be the best coolant. So how to mix, how much water you have to mix with respect to the cutting fluid. That is what I have talked in the previous class. If you see this particular slide where we took the cutting fluid and we mixed range from 1:2 to 1:20. That means that per particular 1 liter of cutting fluid, 2 to 20 liters we have mixed in a ratio or extend. Normally we have done 1:2, 1:4, 1:6, like that. We have increased up to 20 and we used KD2 Pro thermal properties analyzer to measure the thermal conductivity as well as specific heat. If you have seen the thermal conductivity, normally above 8 liters, that is 1:8, there is no much change in thermal conductivity. So if you can go for 1:8 or 1:10 or 1:12, you will get lubrication as well as cooling, because thermal conductivity is majorly function of your water content. Water has a good thermal conductivity, that is about 0.6, whereas mineral oil and biocutting fluid has minimal compared to that one. But among the mineral oil and biocutting fluid, you will have better value for biocutting fluid only. So if at all I want good thermal conductivity, I have to increase water. If I increase water, what will happen? My lubrication problems will come. That's why you need to choose optimum cutting fluid emulsion where water should be used in a better way, so that the thermal conductivity will come as well as the lubricating also should come. The volumetric specific heat is also considerable. So volumetric specific heat should be as maximum as possible. In the previous slide, if you have seen here, normally above 1:8 you will have a good value. Now if you see here, the volumetric specific heat is up to 1:16, it will be gradually increasing. After 16 there is not much. That means that you can go ahead with 1:16 also. So 1:16 if you take, what will happen? You have a thermal conductivity good, at the same time specific heat also absorbing also very good. But if you go slightly below, you may have the better lubricating properties, if and only if it is behaving as a good lubricant. That particular part we will see in the upcoming. We have selected the optimum composition, that is where thermal conductivity is better and specific heat should be better. From this we have considered the cutting fluid composition, whatever the region, whether you want 1:8 or 1:16 and all those things. Now we are going to optimum standoff distance, how far the nozzle has to kept in the machining region. So if you see the MQCF system, distance between machining zone and nozzle position is known as the standoff distance. This is the standoff distance, how far you are keeping your nozzle from the machining region. This distance governed by the mist formation. How the mist formation? The standoff distance is too large, what will happen? Jet flaring will take place. That means that if your workpiece is here, you will have this much only. If your workpiece is here, what will happen? You will have more flaring, that is more diverging will take place. Okay, so for the smaller distances, MQCF may not be completely covered the machining region. Okay. So you need minimum flaring. At the same time, it has to cover your machining region. Since you have already seen the machining region that you are going to talk about is The machining region is approximately like elliptical surface. You have a minor axis and major axis. So even it has to cover that much particular area. At the same time, flaring should be minimum. So for that purpose, how we can decide that what is the stand-off distance, optimum stand-off distance, so that it can cover this machining area completely in terms of minor axis, because major axis how one can cover, that will also we will see that you can take your nozzle, a slit type of nozzle. That means that you have a slit type of nozzle. If you take like this, what will happen? It will cover your major axis instead of going for a hole type of nozzle exit. If you take a slit type of nozzle, then it can cover your major axis. Only this will also diverges from the slit. If it comes like this, that means that my slit is covering my major axis and the diverging in the perpendicular direction cover my minor axis. For that purpose, you have to choose a right type of nozzle. So the selection of optimum nozzle standing distance, how you are going to select, that is, the stand-off distances are varied from 10 to 100 mm with the interval of 10 mm. That means that the experimental setup, if you see here, this is the dynamometer and acrylic sheet is fixed on the dynamometer. Then you are putting your nozzle perpendicular to it and you are spraying with a distance of 10 mm, 20 mm, 30 mm, so on to 100 mm. So as the distance increases, what will happen? At the same time, we have to do this experiment multiple times, because to get the good repeatability and accuracy values. That is what it is recorded multiple times, and average force values are recorded. If you see that one, as the nozzle standing off distance is increasing, obviously the force exerted by spray is going to decrease. If the distance increases, the force decreases. At the same time, flaring, that is diverging, will also get. So this is what you can expect without doing experiment also, but you can say qualitatively. That means it will decrease, that much you can say, but you cannot say how much it will decrease. That is called quantitative value, you cannot say. For that purpose, how much it is decreasing, confirmation one has to do. For that purpose, the experimentation is done. And though it is following the similar trend what we are expecting, now we know what is the stand-off distance versus the force exerted. Now we go ahead with machining area to be cooled. With this force in our mind, we are going ahead with the area to be cooled. For that purpose, as from the part of the force exerted by spray also important for the completely covering the high temperature machining region. That means it has to cover the temperature region. We have seen in the first slide or the second slide where you have a elliptical region of sticking and sliding region. To confirm it, we also do with the infrared camera in this particular slide. Infrared camera is used to measure the thermogram at required area to cool. So if you see the picture, so this is the machining region. I don't know how far you can see this one. This is the headstock and this is the rod, that is the workpiece is here, and your tool interface is in this region. Let me erase this particular section so that I will explain you in detail. So this is what the chip is jumping from the machining region, and this is the machining region. Machining region follows the elliptical, which is also evident from the first picture of this particular class where you have seen the sticking and sliding region. And we want to cool this chip tool interface, which is also proved by this particular thermographical image where you are going to have a elliptical shape. This is particularly the elliptical shape. This region one has to cool. How to cool? For that purpose, selection of optimum spray, which type of spray you want. For that purpose, the first one is flat fan. This is the convex distribution. This is how the distribution takes place, and the shape of the cutting fluid, how it is fall, is given here. Similarly, flat fan even distribution is there. So here the convex distribution is there. Here the flat distribution is there, even distribution across that one. Full cone, normally it is also will have a convex where the full cone is there, and again full cone even distribution. I mean to say full cone means it is like this. The density at the center is very high, and the density goes to the periphery, the density is reducing. Here it is even. Wherever you take, it is completely even. And hollow cone, if at all some of the applications where you are looking, you can have the hollow cone also, where here no cutting fluid and you have on the periphery. At the same time, straight, you will have a point coherent type, but it is cannot be coherent like lasers and all those things. You will have still approximately a point type of thing, that is a circle of small diameter will have. Okay. From our previous literature of the thermographical image, at the same time from the previous experience of the sticking and sliding region, now we have to choose which type of nozzle we want, depend on their area of coverage. For that purpose, particularly for our application, we want flat pan with convex distribution. We can go ahead. So area of spraying, how to check the area of spraying? If you see, for this particular purpose also, since already we have seen a dynamometer is there, on top of it there is a perspex plate is there, on top of it we are just putting a chart and you just spray on it. Instantaneously you just spray and stop it, and you immediately you have to put some focusing high resolution cameras and you have to take the images, because once the spray falls on the chart, it tries to spread in all directions. To get a right image, the photographers should be there in all the directions, and immediately there should be weight and there should be high, without any time they should be catching the images. So for that we have worked a lot, and different photographers are standing on the different directions to measure properly. At the same time, instantaneously the photographer will start before the spraying starts, and it will continuously takes in a spectrum of images, and so that we can take the required image as soon as it fall on the machining region. If you see that one, so the nozzle standing of distance and the minor axis, if you see here the nozzle, just I am talking about the nozzle here, it has a rectangle type of slit, that is whose length is around 5 mm, and because of the divergence it will give me the required type of elliptical shape of the cutting fluid thing. Slit shape is product, elliptical spray is required. For that purpose we have taken the flat pan. So it is evident from the minor elliptical axis that longer than the minor axis. I want the thing should be, the minor axis of my spray should be more than my machining area where the highest temperature is generating, or nearby highest temperature is generating in the machining region. So if you see here, normally at the 30 mm standoff distance, the minor axis covered by the both cutting fluids mist is larger than 27.5 mm. Beyond the standoff distance 30 mm, the exerted spray force gradually decreases. That's why optimum distance is considered to be the 30 mm or getting 27.15 mm. That means from the thermal image we are calculating the minor axis, and the minor axis that I want is calculated from the spraying. From that two things beyond which I won't want, because as your distance increases, what will happen? Force is going to reduce. I want the force also, at the same time I want the minor axis to be covered. For that purpose 30 mm is considered from these 2 points. So you can see here, at the same time minor axis in both we have to consider, because we are going to compare this, that's why we are considering. Whereas if you see mineral oil based cutting fluid, there the minor axis is much less for the same standing of distance compared to your bio-cutting fluid. So even the bio-cutting fluid is giving more minor axis, that will help those temperatures which are surrounded also. So you may get some of the times that why the minor axis for the same pressure it is high, okay? Because of its spreading at the same time, because of diverging for the same pressure. It may have the cutting fluid which is developed in the bio cutting fluid will have more spreading, diverging compared to the mineral oil. How we are going to measure this mineral oil based? If you see here, whenever it falls, we are taking the image. As I said, cameramen are all over covered in all directions, and they are taking the images and they are reporting the images. Okay, I said before the spray starts, they start clicking in a mode where continuously it captures the images, and as soon as it fall, those particular images we are taking for analysis purpose. So mineral oil is there, as well as bio cutting fluid also is there, and you can see the minor axis measurement as well as major axis measurement. Major axis which we are not bothered about, but the minor axis we are taking here. And for the BCF, minor axis is much better compared to the mineral oil based and all those things. The selection of optimum nozzle position. Till now we have seen the composition optimization. We have to optimize the composition so that it will give you the good thermal conductivity and specific heat. Second thing, we have to generate minimum flaring, but it should cover the minor axis of the machining region. For that purpose, we have to play with standoff distance of nozzle from the workpiece or the machining region. That also we have done. So in that we have seen the force exerting, as well as we are also seeing the area covering minor axis. From this we have optimized our 30 mm as our standoff distance. Now we are moving to the angular position, because if I have a machining region, if I put my cutting fluid angle like this, it is not of use. If I can put like this, it is not of use. For that purpose, we have to use optimum nozzle angle, so that in between chip tool interface it should go and it should break the premature chip, or it tries to decrease our minor axis of sticking and sliding region. That is our major motto. For that purpose, how the nozzle angular position will help us. So the nozzle angular position, if you see here, is 0 degrees, from which is a horizontal one. From 0 degrees we go ahead. The testing is done between 15 degrees to 75 degrees, and sometimes it is also done for the 90 degrees also. So nozzle placement must ensure the easy injection of spray into the machining region. It has to ensure that my nozzle angular position should be directing my cutting fluid mist into the machining region, that is chip tool interface region. Penetration of stiff peripheral air boundary layer formed in the rotating workpiece. It has to form a boundary layer on the workpiece. To overcome influence of surrounding boundaries on the cutting fluid, researchers have suggested angular positions are better than horizontal or vertical. So some of the researchers in the literature, they have conveyed that horizontal and vertical are not good. So you have to choose some of the angular positions. For that purpose, the examination is conducted or the comparison is conducted for the different spray angles. Okay. So spray angular position, if you see, the angular position and with respect to cutting force is calculated at different angular positions, and we are going to find where it is minimum. Optimizing the nozzle spray angle position for maximizing the effectiveness, that is minimizing the cutting force, and 15 to 90 degrees is done at 15-degree interval. Normally at 45 degrees it is observed that the minimum amount of cutting force is exerted. Okay. Now, why I required minimum amount of cutting force is another question. I will come to that question. With the increasing of angular position, MQCF spray can penetrate stiff peripheral boundary layer, forming the rotated workpiece, and reduces the cutting force until the angle of 45, beyond which it is going to increase. Till 45, it is decreasing trend. After 45, it is increasing trend. Why I want minimum? If my cutting force, since the cutting force is nothing but you are kicking down the chip. If I send again the force on the tool, what will happen? The tool is already thermally softened. If somebody might have studied about water jet machining, abrasive water jet machining and all those things. If you see the water jet machining, which is an advanced machining process, there the machining takes place or the erosion, mechanical erosion takes place by the water jet. If I have more force, what will happen? Already my tool which is there, which is thermally softened, if my jet is impinging on it, not only the machining operation can remove the material, this also helps in removing the material. That's why it should be minimum. Okay. For that purpose, the experimentation is done and it is considered to be the 45 degrees which is optimum for generating the minimum force, so that with the cutting fluid mist jet which is falling, the erosion on the tool takes place less. For that purpose, we always choose the minimum point, that is here, that is 45 degrees. You can see here three angular positions which are given. One is 15 degrees, another one is 45 degrees, and another one is 75 degrees. How it look like? So, and how the mist is generating on the machining region. If you see for the 45, here the machining region is taking place and cutting fluid mist is falling in the machining region. This is a schematic diagram. To explain the region, how it is falling and other things. So now we have already seen the composition as well as standoff distance and angular position. From that, how we can implement this in a practical situation. And it is not a single parameter that will decide. It is multiple parameters. At the same time, combined effect is another thing to be understood. We have to understand how the nozzle angular position plus standoff distance plus composition play a role, and 2 parameters effect, 3 parameters effect, and all those things also play a major role. For that purpose, just the preliminary experimentation is carried out and we demonstrated how the MQCF is better. For that purpose, workpiece material we have taken the hard steel, which is around 56 HRC. Normally the workpiece is taken, then case hardening is done by some of the techniques. The tool material is taken, that is tungsten carbide tool material, whose coating is done on flank surface. That's why we are concentrating on the crater surface, that is nothing but the rake surface. Tool holder, this is the geometry, and tool geometry is given here, and the workpiece and the tool are given here. Workpiece is tungsten carbide and H13. If you see the hardness, it is 56 plus or minus 2 because it is hardened workpiece. We have taken from the supplier, then we have done the hardening, and then we have done the machining operations for here. If you see the density, Young's modulus, flexural strength, the thermal coefficient of expansion, and all those things are given in the table for your kind reference. The overview, if you see, this is the machine. At the same time, this machine into the machining region, zoom up is done in the machining region here, then this zoom up is done here, so that you can see the cutting fluid mist, how it is falling in the machining region. In this region you can clearly see, and you can also see the temperature measurement. Here it is in the second picture, this is T stands for temperature measurement. Here the dynamometer also is there. This is the dynamometer, and this is the infrared camera is there. Here also it is already indicated. So you can catch up the temperature that is in the machining region. At the same time, you can also measure the forces. That is what I want to show for particular machining applications. Whenever you are machining with minimum quantity cutting fluid as well as flood cooling, this is the two things. At the same time, minimum quantity cutting fluid of the mineral oil as well as bio cutting fluid. How we can compare these four? Preliminary experimentation. So cutting speed, and depth of cut are used in this range, and the minimum quantity cutting fluid and bio cutting fluid are used. If you see here, the cutting force versus cutting speed and flood cooling, FC stands for flood cooling. MQCF stands for minimum quantity cutting fluid. So in flood cooling, two types of cutting fluids are used, that is mineral oil as well as BCF. In MQCF also you have used two types, one is mineral oil, another one is bio cutting fluid. Okay, that should be noted here. Okay, let me erase, because in the next slide you will get all the things. That is about all the graphs will be compared like that. If you see the comparison of the cutting force, what is our requirement? Our requirement should be minimum force that to be generated during the machining operation. For that purpose, if you see the least curve, that is called MQCF for BCF is giving less. That means that whatever if things that I want, which I want to prove, that is coming good. Here also you are going to get bio cutting fluid with minimum quantity cutting fluid is giving better results, because it has a better cooling ability as well as better lubricating ability, so that the tool can maintain its original hardness, at the same time sharpness radius also, so that the forces can be minimum. In other case, minimum quantity cutting fluid with mineral oil slightly better, but the flood cooling is not better, as you have seen in the forced convection and others. Feed forces, similar things are there, but only one noting point here is your minimum quantity cutting fluid mineral oil plus minimum quantity cutting fluid bio cutting fluid. In this range there is a crossover at this particular point. So that means if you want just concentrate, I am erasing this one. If you see this region, the cutting speed is low in this region, region 1 and region 2. If the cutting speed is low, that means my rubbing action is high. That in that circumstances, my minimum quantity cutting fluid with a mineral oil is giving better results. That means that forces are less. That means that mineral oil possesses good lubricating characteristics compared to bio cutting fluids. However, bio cutting fluids having better lubricating properties, because at higher speeds the temperature phenomena will be higher, so it is having a better cooling abilities. That is what I want to convey from this particular The same thing you can also see here, the crossover is there. So same attributes here also. That means biocutting fluid has better cooling properties, whereas mineral oil has better lubricating properties at different speeds. Coefficient of friction also calculated from the equation tan alpha equal to tan lambda plus tan inverse frictional force by the cutting force and all those things. So if you see in this case also, normally MQCF gives better results. That means that friction is less at higher feed rates. If the friction is less or the frictional coefficient is less, that means that my power which is consumed in the machining processes will be used for useful purpose rather than the waste. That is, one of the power that I am giving input is equivalent to shearing plus friction. So the frictional amount will go reduce, means my useful amount of energy in terms of shearing will be high. Sticking and sliding regions, if you see in the flood cooling with mineral oil, normally it is shown here. At the same time, biocutting fluid as well as minimum quantity cutting fluid. This is a sticking region. If you see in the second one, it is clearly shown. This is a sticking region and this is a sliding region. And you can clearly see the sliding marks on this one. If you see the minimum quantity cutting fluid with the biocutting fluid, the sticking and sliding regions are less compared to the flood cooling. You can compare flood cooling mineral oil, MQCF mineral oil, this region as well as this region. This is completely color change and all those things. So that means that flood cooling with mineral oil is not a good option. MQCF can improve even with mineral oil. At the same time, if you see the MQCF with mineral oil as well as biocutting fluid, it gives better. At the same time, you can even see the color change also. It is a red hot region in the mineral oil whenever you are using. You can see in the 3D image how the peaks and valleys are formed in the three-dimensional space. Here in the optical micrographs, you may not see the third dimension, but for that purpose 3D surfaces also taken, but we have shown for the only one application. Sticking and sliding zones, calculated values, if you see, it is MQCF with BCF is much less compared to the other things. It is a minimum. So what I mean to say is biocutting fluid with minimum quantity cutting fluid application gives better results compared to others. For the ecological aspects as well as for the performance point of view, if both things are giving better, why can't we use this as a good alternative? If you see the cutting speed versus surface roughness at the same feed versus surface roughness, both the conditions normally it is giving you the better result. The cutting speed, there is no much change. However, your RA is proportional to F square by 8R. That means that it is proportional to your feed. So as the feed increases, your surface roughness increases irrespective of any type of cooling. However, with respect to the biocutting fluid in the minimum quantity cutting fluid, this gives the minimum value. That means it is better from the point of surface roughness as well as the tolerances. If the surface roughness is better, that means that low surface roughness, surface finish will be very good. That means it will shine. At the same time, the tolerances will be better. That is about this particular slide. Tool rake surface morphology in terms of scanning electron microscope. If you see here, adhered layer is there, adhesion wear is there, and abrasion wear is there. So as I was telling that minimum quantity cutting fluid with biocutting fluid, the lubrication is not that much good, but the lubrication property of minimum quantity cutting fluid with mineral oil is slightly better. That's why adhesion and abrasion is slightly comparable in mineral oil as well as biocutting fluid. But still, if you see the top 4 figures, we are in the better region if at all somebody want to use the biocutting fluids. Summary, So 1:16% oil water emulsion is optimum, that is the composition, because we have seen from the 2 points, one is thermal conductivity as well as specific heat. Thermal conductivity after 1:8 it is stabilizing, so any cutting fluid you can take after 1:8. So whenever you come to the specific heat, there after 16 everything is normal, that is delta, that is change in specific heat is not much. From this particular two graphs, thermal conductivity as well as specific heat, you can go ahead with 1:16 as a composition. 30 mm nozzle stand-up distance is optimum, because you have to generate as much as force, but to separate the chip and the tool. At the same time, you have to cover the minor axis. From the both point of view, 30 mm nozzle stand-up distance is better. The third one is 45 degrees. 45 degrees generates minimum force on the tool, because this is the direction that it has to go. So it will directly impact on the tool, which is thermally softened if you are machining for hours and hours. For that purpose, in a long term, keeping an eye on it, at the same time the cutting fluid should go into the chip tool interface, and it helps by the action of capillary action. At the same time, it has to divert at certain angle where it will penetrate in between chip tool interface. For that purpose, 45 degrees is the good one. Both minimum quantity cutting fluid emulsions are, so bio cutting fluid, next all the things are same. The bio cutting fluid gives better surface morphology as well as surface roughness and other things also very good. That's why from this particular conclusions, we can say that bio cutting fluid is much better from the compared to our mineral oil. And summary of the lecture, we have seen in introduction to minimum quantity cutting fluid, economic way to develop MQCF, commercial nozzles, stand-off distance, or the parameters like stand-off distance, cutting fluid emulsion, nozzle angle and all those things. At the same time, we have also seen the comparison with respect to the practical situation. So this completes today's lecture. So today's lecture is more informative from the point of research. So those people who are interested to take up the research, they can take up by using your own bio cutting fluids. You know what are the bio cutting fluids, since I am talking about many lectures on what are the oils. You can play with the oils, you can mix the oils based on the thermal conductivity. You can KD2 probe you can take, you can measure the thermal conductivity of different cutting fluids, and you can use it, and you can generate your economic way of nozzles, and you can use it. And the dynamometers normally available in the academic institutions, you can use chart and all those things. Spraying nozzle you can develop, or you can even purchase for 8 to 10,000 rupees, and you can check with it. This can be a good work, but only thing is that how to improve the process, how to improve the quality. If at all you are looking from the point of paper publication, how a lot of papers are there, how to improve the quality of your paper, and you can compare with the existing literature, what they have not done, and how I can improve. The most important thing is that how I can improve the quality of your research paper, and how to improve the quality of the standards of the operator. Most important, whether you get a publication or not, but humankind is what the intention of this particular lecture. Even though you are going to give you the good solution for the operator from the ecological point of view, you are protecting the operator. At the same time, you are protecting as a mechanical engineer, as a manufacturing engineer, the performance, that means that the profits of the company. So the bottom line of the story is that being a manufacturing engineer at the shop floor, what you can get from this particular slide is, even though you use the bio cutting fluid, which is economic, which you can make from your laboratory, you can save your operator. As a human, you are doing very good job. At the same time, you are, as a mechanical engineer, as a manufacturing engineer, you are also giving better and better performance to your owner. So profits also you are getting, at the same time you are saving the operator's health and system as well as surrounding pollution also. Thank you.